what did we see till now? If I've given you a mirror, we found out if we keep an object somewhere, where is the image going to form? And what did we need to do that? All we needed was a scale, maybe a pencil, protractor also not required, right? All we can do was just take two rays, extend them, reflect them back and find out where the object image forms, from where the object forms. And we saw that in different cases, the image forms in different places. Pretty simple. But what if we are even more lazy? We don't want to use even pencil, scale, nothing. Given where the object forms, we should be able to tell where the image will form. Just like that. Could we do that? Wouldn't it be nice if we were able to do that? Now, till now, what did we need? Draw a diagram and figure out. Now, forget the diagram. We can do the same thing just by using some math. And let's see what we can do. But the first thing we need before we talk any math is to define something called a convention. What's a convention? Lots of people can do things in many, many ways. Let's say we all in India have decided to drive on the left side of the road. Right? It's a convention in one sense. Because it's going to be a little irritating if each of us decides in our own way, and then it's going to be very difficult to communicate. It's going to be pretty irritating if you think about it. So what we do, all of us get together and say, okay, fine, we'll drive on the left side of the road. Now, there are some countries where they do it on the right side of the road. In fact, most of the countries in the world do it on the right side. But this is one example of a convention. See, most of us sit together and decide, okay, this is how we'll do it. We'll all write A this way and not in some other way. It would be pretty pissing off if we all wrote A's in our own ways and then we had to translate stuff. So that's one of the things we're going to do here right now. What we are going to do is figure out how exactly do we measure these lengths? Because the object is at some length from the mirror, right? Now that's some length and the image might be at some other distance. So all these distances are what we're going to try and connect because that's what we mean by finding out where the image is. So how do we measure where the image is? By giving it some distance from some known fixed point. So let's do something very, very simple. Let's define what's called a convention. Now, we all know that there is a mirror. It could either be this way or it could be that way, concave or convex. Then we'll take the pole of the mirror as what we call our origin, right? And what is the origin? It's the place from which we start all our measurements. Pretty simple, right? And if you have already been accustomed to what's called the Cartesian coordinates, then we know something. From the origin, which is our pole of the mirror, everything else becomes very simple and it's just this, right? Anything right is positive. Anything left is negative. Anything down is negative and anything up is positive. So right and up positive, left and down negative. So if you were to stick to that and any length you measure, just put the signs appropriately, we are good. Because before this, there was a pretty difficult convention where you measured this way in a particular manner, that way. No, it's very simple right now. No matter what it is, right's positive and up is positive, left's negative and down is negative. So with that in mind, the other thing we want to say is all distances are measured from the origin or the pole. It could be a mirror or as you would see in some time, it could also be a lens. It doesn't really matter. So now with this knowledge in our hand, we can jump into and try and find out where images form even without any pencil, paper, drawing, nothing, right? So now that we have the sign convention in place, what do we do to use it? So what do we need though? We're going to derive something that's very favorite, it's pretty dear to most of the people who will ask you questions. It's called the mirror formula. So we all love formulas, don't we? We have to remember this mirror formula. But we're going to make it so that remembering it won't be so mundane to you because you'll also understand where it comes from. So that's what we're going to do today, or in this couple of minutes that we're going to spend. We're going to understand what this mirror formula is. And first, the purpose. Why do we need it? That's the first question to ask, right? Anything you want to know, why do I need it? And why do we need it? To avoid all the other drawings and everything, just calculating out of pure math. Just one formula. It tells you, if you know the object, where's the object? It'll tell you where the image is. If you know where the image is, it'll tell you where the object is. Clean. So now let us see what we can do. Right? Let's take one particular specific case and let you generalize to the other cases. Let's take the case of a concave mirror and you have your principal axis, you have your pole and you have an object over here. The object is beyond 2f. Now let us see what happens and where the image forms by our known method. What do? Take one ray and draw. That's right. The parallel ray is going to go through the focus and the other ray that's going through the center of curvature is going to come back that way. So where is the image forming? There. And that's the top part of the image. This is the bottom part. So that's where the image is going to be. Great. So now what we're going to do is just define some distances. The distance from the object to the mirror is called U. We'll call it U, the object distance. The distance from the image to the mirror is called V. Yeah, just giving them some names. And the focal length, let's call it F. Pretty simple, right? We're doing this so that we can connect these three quantities. What are we connecting? The image distance, the object distance, and the focal length. So once we're done with these three, we'll see how they are related for mirrors. So let's move this aside right now and let's kind of take it up here and let's see how we reason this whole thing out. So let's take Now you can watch there and you can see, I want you to notice that there are two triangles there that have a very special property. And what are those two triangles? Yeah, those are the two. Now look at that. What do you know about those two triangles? Okay, they have one set of opposite angles. The other one is a right angle. Both of them. What strikes you? Two angles same for two triangles. What does that mean about those two triangles? Yeah, AA similarity. If you want to call it by a particular name, it's called AA similarity. Right? Those two are similar triangles. And what do we know about similar triangles? All their angles are equal, but also all their sides are proportional. So let's use our knowledge from similar triangles. Of course, we're going to use math and physics, right? Whatever we learn in math is going to get connected to physics and vice versa and keeps happening that way. So let's see what happens now. Take similar triangles, take the ratio of the sides, and what happens? That side by this side equals this side by that side. Great. So write it down in mathematical form that way. And let's now look again. Why are we doing this, by the way? What struck us? Why did we feel like picking up similar triangles? Yeah, because we know we have to connect some quantities. We're looking for something that relates those quantities, right? We know U, we know V, we know F. How can we relate them? So you found one particular set of similar triangles. Let's look for one more. Yeah, where do you find it? Yeah, look around. There's one more there. Two triangles that seem to be similar, right? Because they have an opposite angle and they have right angles. Great. Now write the same very similar equation for them. And if that's the object size, this is also going to be equal to the object size. So write that equation. It looks like this. And what do you observe? Yes, that's right. Those two quantities are going to be equal. And now with those two being equal, just cross multiply them and see what happens. Right? It becomes a pretty simple thing. One term cancels. Bring it down there. You have a very simple looking expression right now and divide the whole thing by a product. Now, why we're doing this, don't ask me, okay? It just makes it look more beautiful. See, all arguments in physics need not just be for utility, it can also be sometimes for beauty, right? We can be artistic sometimes. So, I'm going to do something pretty sneaky here. Divide the whole thing, the entire equation by UVF. U into V into F. Why do I do that? Because something that looks like that now begins to look like this. 1 by V plus 1 by U equals 1 by F, right? That's how it's going to look. No matter how you want to rearrange it, make it look that way. What is even more important is that one, you don't have to remember this in a very, mugging up fashion because you already know how we get it. Two pairs of similar triangles equate. That's how it will be stored in your mind. And you will learn this. And what do you know about this even more? You know that this will connect image distance, U, object distance, V, and focal length, F. Which means that if you know any two of these, you can get the third one. And you will have plenty of examples where you understand how this is really useful. Makes it so that our old method is too long. So we use this from now on. So that for you is the mirror formula. 1 by V plus 1 by U equals 1 by F. And I hope you understand how it is true as well.